Welcome. You know when you see a game tracking a million players' scores or a spreadsheet that just instantly crunches thousands of numbers? Ever wonder how that actually works? Well, it's not magic. It's all about organizing data. And today, we're diving into the fundamental building blocks of that organization, vectors and matrices.
Okay, so here's our game plan. First, we're going to look at the big problem that started it all, storing lots of related stuff. Then, we'll introduce the first hero of our story, the vector. After that, we'll scale things up to the matrix, which is basically a data grid. And finally, we'll put it all together and see why these things are so incredibly important.
All right, let's get right to it. At the heart of so much coding is this one fundamental challenge. What do you do when you have a whole flood of related data? How do you manage it without everything turning into total chaos?
Let me just ask you that directly. Picture this. You need to keep track of 100 different test scores for a class. How would you actually store those numbers in your program so you could, do something with them?
I mean, you could do it the hard way, right? You could create 100 totally separate variables, score 1, score 2, score 3, all the way up to score 100. But can you just imagine the nightmare of working with that? It's clunky, it's messy, and it just doesn't scale. We really need a better way.
And thankfully, there is a much better way. So let's meet our first elegant solution, a structure we call a vector.
So what exactly is a vector? Well, you can think of it as a super organized container. It holds a bunch of items, but, and this is key, they're all the same type of item. They all live under a single name, but you can get to each individual one by using its unique number, which we call an index. You'll also hear this called a one-dimensional array. It's the same idea.
This right here is the perfect way to picture it. It really is just like a row of connected storage boxes. The whole row has one name, but each individual box has its own number, so you know exactly where everything is. Simple, right?
Okay, so you've got this row of boxes. You're not going to fill them up manually one by one. That would be way too tedious. This is where loops become an absolute game changer. A for loop is the perfect tool to just walk down that line of boxes and systematically place a value into each one.
Let's watch this in action. The loop kicks off and our index I starts at 1. The program asks for a number, you type in 95, and boom, it's stored in the first box x1. The loop cycles, I becomes 2, you enter 13, and it lands right in x2. This just keeps repeating, automatically filling each box one after the other. It's a really clean, efficient process.
Now that our data is all neatly organized, we can do some really powerful things. Let's say we want to find the smallest number in our list. The logic is actually pretty clever. First, you just assume the very first number is the smallest. We'll call it our champion. Then you use a loop to go through every other number in the list and compare it to the champion. If you find one that's smaller, it becomes the new champion. By the time the loop is finished, the last one standing is the true minimum value.
So, we've mastered a single row of data, but what happens when our data isn't just a list? What if it has both rows and columns, kind of like a spreadsheet? Well, for that, we need to level up to the matrix.
A matrix is basically the next step up from a vector. It's still a collection of variables. They're all the same type, and they're all under a single name. The huge difference, though, is that it's multidimensional. So to find any single element, you don't just need one index, you need two. You need its row number, and you need its column number. The spreadsheet analogy is absolutely perfect. Or think of it like a game of Battleship. You can't just call out a number, you have to call out a letter and a number, like B5, to pinpoint a specific square. Every piece of data in a matrix has that same kind of two-part address.
So, if we used one loop to fill our one-dimensional vector, how do we fill a two-dimensional grid? Well, you guessed it. We need two loops, one nested inside the other. We use an outer loop to go through the rows one by one, and for each row, we use an inner loop to go through all the columns in that row.
And here's how that works in practice. The outer loop picks a row, say row number 1. Then the inner loop takes over and just zips across all the columns in that one row, filling them with data. Once that whole row is full, the outer loop moves on to the next row, and the inner loop does its thing all over again. It's a really systematic way to sweep through the entire grid.
Okay, so here's a question for you. We just figured out the logic for finding the smallest number in a vector. How would you take that same basic idea and adapt it to find the largest number in this entire matrix?
And here's the beautiful part. The core logic is exactly the same. You start by crowning the very first element as the largest. Then you use those nested loops to visit every single other cell in the grid. Anytime you find a number that's bigger,
it takes the crown. It's the same powerful algorithm, just supercharged for 2 dimensions.
Okay, we've seen what vectors and matrices are and how to work with them, but let's just take a step back and really focus on the why. Why are these structures so fundamental to programming?
So when should you use one versus the other? It really all comes down to the shape of your data. If you have a simple list, like the top 10 scores for a game, a vector is your go-to. But if your data has rows and columns, like a seating chart or a game board, a matrix is the perfect fit. It's all about choosing the structure that mirrors the real-world thing you're trying to represent.
This quote absolutely nails it. Vectors and matrices are your secret weapon against data chaos. Instead of trying to juggle hundreds or even thousands of individual variables, you have one single, elegant container. This is what lets you write clean, powerful code that can handle huge amounts of information.
So, let's sum it all up. These structures help us organize our data in a logical way. They save us from the absolute nightmare of declaring countless variables. They work perfectly with loops, which lets us build powerful, repeatable algorithms. And at the end of the day, they form the foundation that allows us to solve truly complex problems with clean, efficient code.
And that really brings us to our final thought. You now understand the basics of organizing data in lists and in grids. So just think about it for a second. From analyzing weather data on a map, to building a chess game, to tracking inventory in a warehouse, what kind of real-world problems could you start to solve with these tools?